We can use what we know about integrated rate laws to analyze kinetic data for a particular reaction to determine the rate law of the reaction. So let's imagine how that would be done by using this particular reaction between a blue dye, shown here, and we're just going to abbreviate this as BD for blue dye, and bleach, which is sodium hypochlorite. And when they react, they form colorless products. So this is blue. It has an absorbance at 630 nanometers. And as the reaction proceeds, the color fades, and so the absorbance at 630 decreases. So we can follow the time course of this reaction by following the absorbance of the blue dye as a function of time. And when we do that, we get data like this. Note that when this reaction occurs, both the blue dye and the sodium hypochlorite, or the bleach concentration, decrease in time. So they're both changing in time. And so when we do this experiment, if we're not careful, we will have two variables, two concentrations, that are changing as a function of time. So we want to think carefully about how to set this experiment up in such a way that we can keep one of these concentrations the same over the course of time for any given curve or trial that we do. So the way that we do this is to use a blue dye concentration that is going to be fairly small. So we're going to always start with about 5 times 10 to the minus 5 molar of the blue dye concentration. And what we're going to do is we're going to vary the bleach concentration. And we're going to vary it, but we're going to have this concentration, the concentration of the bleach, sodium hypochlorite, be much, much, much larger than the blue dye concentration. So in each of these curves, we have a different bleach concentration. So for this one, it's 0.11 molar. For this one, it's 0.27 molar. And for this one, it's 0.42 molar. Now, how this is going to work is the blue dye is going to be the limiting reagent because it's many, many orders of magnitude smaller than the amount of bleach that I have in my system. So the maximum amount of bleach that I can use up in this reaction, which is 1:1, is going to be 5 times 10 to the minus 5. So if I think about the amount of bleach that I started with, subtracting the amount that I use up, I essentially still have the amount that I started with, because I'm going to use up such a small amount of bleach that this bleach concentration is going to stay constant throughout this entire time course of this reaction. For each curve, the bleach concentration changes, but within a given curve, I can assume that the bleach concentration stays the same as whatever it was at the beginning of that reaction. This type of reaction conditions are called flooding. So I've flooded the reaction with bleach. Or sometimes we call this pseudo-order reaction conditions, because what this is going to do for us is to make this reaction look like a reaction which has the same reaction order as the blue dye. So if you think about it, the rate law should be equal to some rate constant times the concentration of blue dye raised to some power times the concentration of bleach raised to some power. But if I keep the bleach concentration constant, the K is also a constant value. I can lump these two variables together into one variable, which I'm going to call K observed. And then the rate is going to be some constant, which I'm going to call K observed, times the blue dye concentration raised to its power. And so what I've done is I've reduced my problem from a 2-variable problem to a 1-variable problem by keeping one variable constant by flooding with that particular reactant in the reaction. Next, what we're going to do is remember that the rate of reaction is equal to the opposite of the concentration of blue dye changing in time. So because what I'm measuring is the blue dye concentration, this absorbance is the absorbance of the blue dye, so I'm measuring the concentration of blue dye as a function of time, I'm expressing my rate in terms of the derivative of blue dye with respect to time. That should be equal to my K observed value times the blue dye concentration raised to the order of reaction with respect to blue dye, or N. So now I can think about all the possibilities for N. So if N is equal to 1, I have a first order reaction, and my integrated rate law tells me that that reaction should be exponential, or look like blue dye is equal to blue dye at the beginning, e to the minus K observed times T. And if I take the natural log of both sides of this equation, then the natural log of the blue dye concentration divided by blue dye at the initial point should be equal to minus K observed times time. So notice that I have divided both sides of this equation by the initial concentration of blue dye and then taken the natural log of both sides. So that tells me that the natural log of the absorbance, which is proportional to the blue dye concentration, divided by the initial absorbance, the absorbance at time t equals 0, should be proportional to time in a linear manner with a negative slope equal to K observed. On the other hand, if the order with respect to blue dye is 2, second order, then my integrated rate equation looks a little bit more complicated, and I have that the blue dye concentration will be equal to the blue dye concentration at the beginning divided by 1 plus K observed times T. And so if I take the reciprocal, let's first do the same thing. Let's divide both sides by the initial concentration of blue dye. So if we do that, and then take the reciprocal of both sides of this equation, so we have blue dye naught over blue dye is equal to 1 plus K observed times T. Then we can see that 1 over the blue dye concentration at any time, or the absorbance at any time, will be proportional to the rate constant T. So in this case, if our order is 2, we'll find that 1 over the concentration, or the absorbance, will be linear in time. So we can try making a graph of natural log of the absorbance versus time, or 1 over the absorbance versus time, and see which one of those two graphs is linear. The one that is linear tells us the order with respect to blue dye. It only tells us the order with respect to blue dye because it's the blue dye concentration that we've been observing to look at our rate. That's the concentration that we have allowed to change over the course of the time. So in the case of these curves, if we graph the natural log of absorbance divided by the initial absorbance, we get the following straight lines. And you can see that they're very nice, beautiful straight lines. And so we can pretty confidently say that the reaction is first order with respect to blue dye. Now we still don't know how the reaction behaves with respect to the sodium hypochlorite or the bleach. But we can use our data from here to determine how the bleach affects the reaction rate. So the slope, which is negative, down, over, so the opposite of the slope is equal to K observed. Remember, for this first order integrated rate equation, we had that the natural log of the absorbance divided by the absorbance at time t equals 0 was equal to minus K observed times t. And so minus K observed is the slope of each of these lines. So we have a K observed for each of the concentrations of bleach that we used in this experiment. And so the next thing we're going to do is to see how this K observed depends on this bleach concentration. We can see that it's bigger for the larger bleach concentration and smaller for the smaller bleach concentration. Remember that our K observed was a combination of the true rate constant times the concentration of the sodium hypochlorite raised to the order of reaction with respect to the sodium hypochlorite. And so we're going to make one more graph. So the slope, remember, of these lines is equal to minus K observed. So I get a K observed value from each of the trials that I have done with different bleach concentrations. So if I know K observed and I know the bleach concentration that I used, then I can graph the K observed values as a function of the concentration of bleach that I used. If this order is 1, that graph will be linear because this K observed will be linearly dependent, order of 1, linearly dependent on the sodium hypochlorite concentration. If this is 2, then I expect to see a parabola, right? So I expect to see K observed proportional to the square of the concentration, and that's a parabola. Typically, we don't get orders that are too much higher than 2 or 3, but you can imagine that if this is third order, I'm going to get a different shape of curve. And so if I graph K observed as a function of the bleach concentration, and do that for a whole bunch of different bleach concentrations, you can see that I get a very nice straight line. And so the order must be equal to 1 because it's linear. So the linearity tells me that that the m value here is 1 because that gives me a linear equation. Furthermore, the slope of that line, y equals mx plus 0, this should go through 0, 0. The slope of that line is my true K value. So the equation that fits these data is K observed equals 0.25 per molar second times the bleach concentration. And so my true K value is 0.25 per molar second. So finally, I can write that the rate law for this reaction is K times the blue dye concentration raised to the first power, because I can see that the first order integrated rate equation fits my blue dye data. Natural log of absorbance versus time is linear, so it's first order in blue dye. And then it's first order in sodium hypochlorite in the bleach because I get a linear equation when I graph K observed versus the bleach concentration. So it's linear. And my K value is 0.25 per molar second.